limit cycles, we see that it's at some random place in R. It's not going to 0. It's some place RC that used to be a kind of slow region. And its frequency is whatever the frequency happened to be as you were going around here. It doesn't have, the frequency doesn't go through 0. It doesn't go to infinity. It doesn't do anything special. It's been doing this. And the R is at some place where the function, R dot, just happened to be kind of slow near RC. So you're not going to see the amplitude, the R value, is not growing from 0. It's wherever it happens to be. And the frequency is not going from 0. It's wherever it happens to be. So that's what's meant here in this chart by order 1 and order 1. They're just values. Now they're going to vary, but they're not going to go, up like that or down like that to 0. They're just going to be what they are. Then there was the saddle node on the limit cycle. That's the one that's illustrated in the right-hand portion there. And that one is something that doesn't happen in R. You notice the R value is staying about where it is. It's not, the R value is not growing from 0. It's the frequency that is special, because this used to be here, before the limit cycle was formed, it used to be a steady state. So it better be slow. Here it didn't used to move at all. It had a 0 here. It was a steady area. You would go here and you just stay there forever. Okay, so now you're not going to stay there forever, but you're going to stay there a very, very, very long time. And that's what's being shown in this picture. Okay, it's not a steady state, but you might think there was a steady state if you didn't wait long enough. And then otherwise, no, it's not a steady state. It does this. So you're going to see this behavior not in the amplitude, not in the radius, but in the frequency. The period is going to go to, the period is infinity as at the point of bifurcation. At the point of bifurcation, that's when you cease to be a steady state. When you were a steady state, the period was infinite. So the period is not infinite afterwards, but it's very, very big. And now finally, there's one more that I didn't quite show you. I just want to complete it. It's the one I know the least about. That's why I didn't show it to you. Because I've never come across it. I happen not to come across it in my work. And that is when you have a limit cycle which runs into a saddle. And when the limit cycle runs into a saddle, it dies. And so since it's running into at a saddle, your behavior is very slow. Remember that on a saddle, if you're really on the saddle, you stay there forever. It's a fixed point. If you're a little bit off a saddle, you leave it because it has exponential growth in one of the directions.
Any reason it's called homoclinic?
Because, yes, thank you. Okay, there are two special kinds of cycles, one called heteroclinic and one called homoclinic. Homoclinic is a cycle which is anchored at a single saddle where you leave the saddle and then come back to the saddle. As you can imagine, if it's exactly homoclinic, its period is infinite. It must be infinite because you stay an infinite amount of time here. This is a fixed point. If you're really on it, you stay there forever. Over here, you don't stay there forever. It is a perturbation. You're away from this and you grow, you go at some speed, but you go pretty slowly. But this is a homoclinic cycle. It comes back to itself. Heteroclinic cycle, there would be two such points. You would start off here and you would take an infinite amount of time to get at that point, which you would stay at an infinite amount of time, and then you would come back after infinity. So it's twice as long, two times infinity, come back. This one is only one time infinity long. And that's why it's called a homoclinic cycle. Thank you. And this is called a homoclinic bifurcation when you have a limit cycle, which lived in here, and it is touching at last. It's growing until it touches the saddle, and that kills it. It explodes.
And what happens as you go up into the top of those diagrams?
Those are the points yes, this is successively as you increase mu. Over here you had no fixed points. At this point, this is a saddle node bifurcation where you are creating this stable and unstable points simultaneously, and here they're about to leave each other. And Yes, and then this trajectory runs into the saddle. Thank you for asking for these details. So again, if you had experimental time series and you wanted to know, because generally you don't, I mean, it's all well and good to write down these systems, and that's good for pedagogical purposes, but if you're running some big experiment or some big computation, you don't have little equations like this. You have Navier-Stokes, you have earthquake equations, you have, you have whatever. You're running some big program, you're doing the real thing, and what these things should represent to you in your mind are when you plot two coordinates, two aspects. You plot the fluid at this point and the fluid at that point. You plot the temperature at this point, the temperature at that point. That's a projection of the phase space, which will generally give you behavior that looks like this. Almost any projection will do. So you'll see that, and you can measure things, but what you won't have is little tiny equations like this. You'll have pictures like this when you plot two variables, one against another, that are your output. You will also have, as you change your control parameter, you will have a single quantity, like the period, like the amplitude, and how it will vary. And you'll have those things, and with all those things, you act like Sherlock Holmes. You eliminate the possibilities, because there are not so many possibilities, and you will say, oh look, what I have must be a homoclinic bifurcation because my period varies like the log of the distance from the bifurcation point. And yet my amplitude does not change very much, or you'll say something like that.
What if one does not have time resolved data?
You mean you can't vary inside you?
So in your example there, where you're able to trace it around.
Yes.
Very curious problems where we'd like to do this, and if there's no time resolution, so it's simply just snapshots of what the system is doing, and if you plot two variables like you have on the
Previous one, yes.
next slide, or wherever that was, you will just simply get the entire screen filled with points.
You have entire what?
It will fill the entire screen because it's traveling everywhere in the phase space.
Yeah, I don't know. Possibly some of the other, can you tell me more specifically what it is?
Well, for example, PIV data,
Yes.
which is just snapshots, but not time resolved,
Wait, nowadays, why aren't you doing time resolved PIV?
because it's supersonic.
Oh,
I was just curious.
yes. I don't know.
Okay,
Sorry.
that's all right. I was just curious and I'm going to find out.
Yes, it's true. I'm acting as though you could always do something like
So yeah,
that.
if like I like the Sherlock Holmes, like looking at it, and we have looked at it, but when I plot those sort of things, because I have no ability to literally trace
Yeah,
the red line
yeah,
on the
yeah.
page,
Yeah.
it's just filled.
Yeah.
And
You
there's
don't have time
nice
as a,
little residue plot or anything like that, or figures or anything like that. It's just. And
Yeah.
I wondered if there was some
Maybe.
true way of observing.
maybe
Maybe there is.
Maybe there is. Yeah, sorry. And what's the situation? Is it a jet or is
Yeah,
it
supersonic jet.
a supersonic jet? Yeah. Yeah, I don't know.
Does it qualify as a dynamic system?
Oh, of course, anything
Yeah.
is a dynamical system. But is it, okay, the right question there is it useful to study it by the methods of dynamical systems? It could be that it's not.
So these jets have many modes that they can sort of fall into, and they will get stuck in one mode or get stuck in another, and that's why.
Well, in that case, maybe so, if you use that kind of language.
Yeah.
I think a constant debate, that I don't know anything about, but I'll go to something I do know about, is a transition to turbulence. A constant debate is how does dynamical systems relate to transition to turbulence? And that has gone through many different fashions, which by now I'm old enough to have seen. There was the fashion of transient growth. There's currently fashion, well, again, I'm not going to prejudice because I don't know, of there being many, because this one's still in the making, many unstable periodic orbits, many unstable periodic orbits, and is turbulence visiting many unstable periodic orbits in heteroclinic or homoclinic ways. Some people think that that's what turbulence is. Other people think that's not at all what turbulence is, and they think it's something called directed percolation, which I might talk about in the end of the class, perhaps next week. That's Dwight's current work. There was another time when it was thought that transition to turbulence, and this was in the late 70s, was when you had stability to two-dimensional, I'm talking about now in space, two spatial dimensions, perturbations, but instability, but if you were away from the equilibrium in 2D, you were unstable to 3D perturbations, and that was Orsag and Patter's work in the late 70s. And there was also a fashion of strange attractor is transition, is turbulence close to transition? Does it take place in a low number of dimensions where you could compute things that are like eigenvectors, but that values that are called Lyapunov exponents that take place in chaotic behavior? But that fashion seems to have died down as well. Notice I'm not using the words of is it true or not. I'm using fashion words because it's not known yet what it is. Or, I mean, each of the proponents, it will be known what it is when everybody agrees what it is. If each of the scientists say, oh, one of them says, oh, I know what it is, it's this, and I know what it is, it's this, and I know what it is, it's this, and they can all get published, then that means you don't know. And that's the current situation. So the application of dynamical systems theory to transition to turbulence is not clear. This may also be the case for your problem as well. I don't know. Here there are ideas for things like supersonic jets of doing stability analysis about the mean flow and finding the unstable modes of the mean, which is not really justified because you're generally doing stability analysis about a fixed point, which is what we were discussing here. Why would you do instability analysis about a mean? So that too that's currently fashionable and maybe is true. So I don't know, I'm talking around your question. You know.
That'll work.
What were you plotting from your POV data that you pushed
It could be, well,
in? Sorry, we digress, but
Yeah.
go on.
a variety.
So you weren't plotting velocity fields?
No.
What were you?
Well, we decompose the flow into proper orthogonal decomposition modes, and then entry points, for example. And then looking back at the snapshots that correspond to those in phase space, have some sort of like pseudo time. Yeah, it was just a question.
Yeah,
Sure.
I mean, in fact, I'd like to perhaps then invite other people to say what they are studying in particular and ask what dynamical systems could or could not do for them. Anybody have, you were speaking about these chemical systems, you have some specific thing?
Yeah, transition in the pipe, turbulence.
Oh, you're talking about transition to turbulence, then, okay. Okay, transition to pipe turbulence, I think I could speak about perhaps next week. I could make a new class on these different modern approaches to that. It would be mostly kind of historical. Here, I feel this is a finished field and everybody knows, if you ask a question and if I don't know the answer, I can find it in some book. But transition to turbulence is not a finished field. I can say what are the different approaches, but I can't say which is right. Anybody else have something they would like to, some particular physical or chemical or mechanical or biological or geological or astrophysical object they wish to bring up? It's a little, I feel this thing about transition to turbulence or other things too, it's a little like, I think, people say they want to solve turbulence. What does that mean, solve turbulence? I feel you'll know what that means when you have the answer. there isn't a question. There'll be an answer, and then the question will be clear that you answered. And the situation, it seems to me, it's a lot, again, some people, I feel there's a lot of confusion. For transition to turbulence in particular, you can do Navier-Stokes simulations, that's what I do, it's what these people do, and you can reproduce turbulent behavior or supersonic behavior, if it's sufficiently low Reynolds number, sufficiently simple geometry, quite well. You reproduce it perfectly, pretty much. So does that mean you've solved it? You've reproduced it, with the equations. You have a theory. That theory is called Navier-Stokes, or Mach numbers and this and that. That's your theory. But I think that the answer there is that's not what you're looking for. Before statistical mechanics did not really introduce new physics, it introduced new mathematics. Newton's laws, statistical mechanics is not relativistic. It doesn't say anything about quantum mechanics. Statistical mechanics, okay, with Newton's laws, you can take a zillion, million, billion, trillion particles and bump them against each other and have them collide. And if you knew the initial conditions of a zillion, million particles and all their initial velocities, then you would know where they would be later. But what does statistical mechanics do? It reduces, and that's really not what you want to do. I mean, you could do that, and have you solved it? Well, in some sense, yes, you have equations that do the same thing as the particles. Your equations, so that's, your head that you made the equations. But what statistical mechanics did is it said it reduced those zillion, million, billion into fewer equations, into make you be able to think better about it. And so that you no longer use Newton's laws, or you never did because they didn't have computers then, to solve the equations with a zillion, million, billion particles all bumping each other. You don't need an infinite amount of data for all the different initial conditions. You have some different way of thinking about it. And so too, with turbulence and transition to turbulence, computers can do it all. That shows Navier-Stokes is right. Oh, good. But that's good. We didn't necessarily know that. It could be that there was some other. It's not. So I think Navier-Stokes is not. Okay, to me, in some sense, I don't know what physics and math is, but to me, in some sense, statistical mechanics is not new physics in the way that quantum mechanics and relativity is new physics. I could be wrong, but to me, because I don't know physics that well, but to me, statistical mechanics sits on top of Newtonian mechanics. It tells us how to rearrange those quantities. And so, too, we know everything about fluids because we know Navier-Stokes. But what we want is a rearrangement of that theory that makes it simple, that takes out the basic things, that makes it predictive, that makes us do something other than turn the crank with a zillion, million, more and more resolution and more grid points. We want something...
Or framework
a different framework. That's not new physics. It's not effects that are missing. It's a way of understanding. It's a way of post-processing. Or pre-processing, or something like that. It's some pure thought kind of thing. Unlike, say, quantum mechanics and relativity, which needed new data that contradicted the old equations. Right? The whatever that thing with the perihelion of Mercury, it was wrong without the relativity, and whatever they do with quantum mechanics. Say, I don't know these things very well, but whatever they did with quantum mechanics, they had wrong answers until they put in the quantum mechanics. But that's not the case for Navier-Stokes. Navier-Stokes equation gives the right answer for all the turbulent phenomena that we know about, and the supersonic phenomena, and so on. We just don't like that we have to think about it with a zillion, billion particles and more resolution. We don't like that aesthetically. And in the past, we humans have been able to do better than that. We've been able to simplify and get at the essence of things. And so we think we can do it again.
Maybe we can.
Maybe. A lot of people think they can, anyway. So, let's see, it's 4:30, and the classes are supposed to go on to 5. I want to ask a vote. Okay, so what did I come with? I have something like 8 or so classes that take 3 hours or so, 2.5 hours, that I usually give. I'm giving 7 classes here. I have 8 classes, but they do not include things like transition to turbulence or computational fluid dynamics. They go on with dynamical systems and pattern formation and things like that. I can go on speaking till 5 and start the next class and thus get further. And then maybe get and add more things at the end, or I could cut off the dynamic. I can do all kinds of things, as long as I have enough preparation. Shall I continue and give the first part of my next class, which is on convection? Or should I stop here, which is a kind of stopping place? Do you want to see things that are not in this dynamical systems class at the end, things about transition to turbulence or about computational fluid dynamics?
Yeah, I
Who
think,
wants to continue?
I
It's
think
okay?
most people here have got a fluid
Yeah.
mechanical viewpoint, and they'd like to see those things
Yeah,
dealt with.
okay.
Probably, well, that's my guess, sorry, I'm speaking for myself. As you-
So, we'll go on to the next. I never know, people say to speakers, oh, you must be tired. No, the speaker is never tired. And how can you tell? Well, who falls asleep in class? Is it the speaker? No, it's the students. To speak is easy. It's to listen that's difficult. That's, right? Hence, this question of whether you can, let's see, yeah, to listen is difficult, to speak is easy. Let me find my class.